Greetings, AP Calculus students. Mr. Record here from Avon High School. We're going to take a look at our example number 2 from my hypothetical topic 812 part B of the College Board course and exam description. What I do with my course in our BC course, which is a second year uh, continuation of Calculus AB, is I'll talk about some methods of finding volumes of solids by using the shell method, which is not something that is specifically tested on the AP Calc exam. However, it could be used if you deem it to be a little bit quicker. And of course, for those of you that might be taking Calculus 2 in college, this is something that you're certainly going to see in that environment. So without further ado, let's take a look at our problem. Let's move me out of the way. So we're going to look over here. So it says find the volume of the solid formed by revolving the region bounded by the graphs of x equal e to the negative y squared power. The vertical, or I should say horizontal lines, y equals 0 and y equal 1, but we're in between those lines, thus due to that inequality. And of course, the y-axis and x-axis are going to be our other boundaries. And it does say to sketch the graph and draw representative rectangles. Well, I want you to know that this is a problem that you would very likely, A, either be provided this graph from the very beginning, or B, you would be allowed to use a suitable technology that will enable you to sketch that graph. And the graph, the function that I'm talking about, no doubt is this one. That thing was probably scaring you, right, from the very first moment you saw it. I'll be honest, I would not know how to sketch that graph without using technology. So the technology that I'm going to use is going to be the TI Inspire, which it might be worth mentioning that if you were going to use the TI-84, I think this might be a little troublesome because you would need a little bit more robust calculator. So maybe you could use Desmos or some other kind of utility that would allow you to graph what's really called a relation. And so what I'm going to do is I'm going to change in my TI Inspire from my graph menu in the scratch pad, I'm going to change my graph entry from that of a function to that of a relation. Now I can physically type in this equation exactly the way that it appears on the page. X equals e to the negative y squared power. And once I hit enter, the calculator will do all of its wonderful magic and it will re-render this function that looks kind of funky, right? It looks a little interesting. It looks like the y-axis is playing role of a vertical asymptote, and perhaps the 0.01 does lie on that particular graph. So all I'm going to do is replicate that graph back to my page, but I'm not going to worry about drawing this perfect Picasso drawing, this perfect Rembrandt, this perfect Van Gogh. I don't know, I'm running out of artists here. But I do know that eventually I'm going to have something that would look like this. Now notice that there's a bit of a scale change going on here, and I'm not really worrying so much about are my points and such accurate in this region, because I really don't care. The whole point of this picture is just so that I have a visual so that I can draw my representative rectangles. And so I feel pretty good that that's going to do the job for me. Now I'm going to go ahead and graph these other equations. The y equals 0, well, that's just the x-axis, which is kind of playing double role because I am using the x-axis as a boundary. And then if I graph y equal 1, that's up here, the horizontal line. And then of course the y-axis, I'm going to throw that here in purple. I think it's very safe to say by the time that every one of these expressions or ideas or inequalities or equations are sketched, we have ourselves a nice enclosed shaded region that would be depicted by this yellow space that I'm going to now throw in here. All right, so that would be this enclosed region that will represent our sort of home base, I suppose, our our two-dimensional space that we're going to revolve. Okay? And we are going to revolve about the x-axis. Well, that's going to be awful convenient. Maybe I use a dashed line to kind of convey that. So this lower boundary is going to act as the axis of revolution as well. So there we go. All right, now, if you recall back to the days of the disc method, washer method, things are a little bit different now because we really would hate to use disc washers for two reasons. And the reason is because, one of them is because right about here, there will be a change in our philosophy between which equation is on top versus which equation would be on bottom. So we would change from this horizontal line to the actual curve, which means we'd have to use two integrals. And this, of course, would be a disk method, which isn't so bad on the surface. But excuse me, but when you start thinking about what the top boundaries are and the fact that we would have to integrate with respect to x, we start getting a little bit put off by trying to use a disk method. And so therefore, I am not going to go down that road. All right, instead, I am going to say, let's go ahead and attack this problem from the standpoint of shell. And so I'm going to get rid of that rectangle or that dash line. And when I do the shell method, and if you didn't get a chance to catch the example one video, you might want to check that out because I go into a little bit more detail about the development of the shell method. But in our shell method, all we have to do is draw a representative rectangle so that it is parallel to our axis of rotation. And so that would be a horizontally drawn rectangle, as you see right down there. And so once that rectangle is spun around this axis of revolution, you have this hollow tube, so to speak. And in this hollow tube, you're going to stack more tubes inside of it, more tubes on the outside of it, and then all of a sudden we've got three-dimensional space that we can find the volume of. How cool is that? And so once again, the formula for the volume using the shell method has the 2 pi coefficient. Again, check out the video before that goes into more detail. We're going to integrate between a couple of boundaries. I'm going to use C and D since they're going to be y values. And then we use what's called the radius in terms of y times the length of the rectangle in terms of y. Why are we in terms of y? Very easy. If you use your finger and thumb to size up the width of the rectangle, hold it up to the camera there, that's a change in y. All right, so anytime that you draw a horizontally drawn rectangle, you're going to always do your integration setup with respect to y because that's the width. All right, so again, this is acting as the radius, and this guy is acting as the height or length, if you want to refer to it as such. All right, so let's get it going here. So we have our 2 pi integrate. I'll worry about the boundaries in a bit. The p of y is just simply the distance that we are going to travel between the axis of rotation and our representative rectangle, depending on where you want to draw it. You could have drawn it anywhere in this yellow space. Well, because you're using the x-axis as sort of a measuring point, this distance is very easily going to be called y, right? Because it's just an arbitrary distance away from the x-axis. And so we have a pretty easy setup here for the p of y, which is nice. And then for the h of y, you just simply take the right side of that representative rectangle. That would be the expression e to the negative y squared. And then you take the left side, which is just x equals 0, and you would subtract. Right minus left is the way that you find the length of a horizontally drawn rectangle every time. And so right minus left would be e to the y negative y squared minus 0, at which point I'm not going to worry about subtracting 0 because it's kind of a moot point. Then I can toss my dy in there. And then, of course, we're going to look at our boundaries or limits of integration. They start here at the bottom of the picture 0 and go all the way to the top of the picture, which is the value 1. Remember, those have to be y's as well. All right, and with that, we have the setup for our shell method. What we can do very quickly is integrate this by hand because this one's not too terribly bad. It will use a u substitution. U would be negative y squared. That would be the complicated exponent there of the e. The derivative of that u with respect to y is negative 2y, and then I can swing my dy over. And of course, we are very happy that we have a y dy in that integral because there's a y dy in our integrand. We are not so thrilled about the fact that there's a negative 2, but we can easily fix that by flipping it upside down, if you recall the shortcut to handling that. So we have the 2 pi in front. There will be a negative 1 over 2 coming out in front because of this guy. And then we're just really integrating e to the u with respect to u. Now, at this point, we could make a decision about whether or not we want to change the boundaries to use or use the original y boundaries. I'll tell you what I'm going to do. It doesn't seem like it's going to be so tough. I'm going to go ahead and say, let's go into our u expression here and evaluate the u for the value of y being 1, and we get negative 1 squared, which is negative 1. And if we do the same thing for the boundary of 0, negative 0 squared is just going to be 0. Now keep in mind that negative does not get absorbed into that squaring process, so that's why it would stay as negative 1. And so I think we can then replace those boundaries, do a little bit of simplification out here in front to cancel the 2's. If we integrate e to the u, one of the easiest integrals in the world to resolve, it is e to the u. Upper limit is negative 1, lower limit is 0. Let's factor out that negative pi and plug in those boundaries. E to the negative 1 minus e to the 0. And then if we were to just play around a little bit with these, I believe it looks like on the surface, it's like, oh my gosh, we're going to get a negative answer for volume. That can't happen. Well, I don't think that's going to be the case because e to the negative 1 is the same as 1 over e, and then e to the 0 is 1, and I am pretty certain that this quantity in here is indeed a negative result, which once it multiplies by that negative in front, we are going to get a positive. Now, there is another way that you could approach this, and if you wanted to, you could factor out a negative just to make it look prettier. Factoring the negative out will wipe out this negative. Each of these two signs would change, at which point I could just do a little flippy flop and call it e minus 1 and call that the answer. I could also get a common denominator, but you know what? We've put enough time and energy into this problem that I think the point is made about how you can use the shell method to resolve the volume of a solid that's got a pretty nasty relation here. Anyway, I hope this helps out. We got a few more videos over the shell method that you are more than welcome to check out to just get a little bit more confident with this procedure. Anyhow, we'll see you next time.